Welcome, dynamic students. This mini lecture will cover principles of what's called general rigid body planar motion. In some of your earlier examples, we've dealt with quite a few bodies that had some point somewhere that wasn't moving, that didn't have any velocity, that had a point of fixed rotation. So the center of something that was rotating, and that center was fixed relative to an inertial reference frame typically. In this case, nothing is sitting still. Every point on the body is moving somehow, and in addition, of course, the body is also rotating. So what we have is we've got a wall and then a floor or some kind of a flat surface. It doesn't look quite flat in the sketch. This is a ladder, and it's a rigid body, and it's sliding down the wall, and the bottom of the ladder is scooting out. So this is a typical safety problem that you want to avoid, and it's usually why you have like a little rubber feet at the bottom of your ladder, and you've got some safety rules about how you position the ladder. So somebody didn't follow the safety rules, and hopefully nobody's standing on the ladder. So the ladder is falling. And so point B is sliding down the wall, and it's important, it is sliding straight down the wall. It isn't rotating out from the wall, it's sliding down the wall. And we know its velocity and its acceleration and and magnitude and direction at point B. We know that the ladder is 16 feet long, and somebody wants to know what's going on at A, motion-wise, velocity and acceleration, at the point shown, and then what's the angular velocity and acceleration of the ladder as it's the rigid body. And the point shown is the point in time at which that angle is 30 degrees. So this is going to be another, we're going to use our equations of motion for rigid body planar motion. We're going to relate acceleration at one point to acceleration at the other, and the angular acceleration of the body, the radius between the 2 points, minus the angular velocity squared times the radius, or applied in the direction of the radius between the two. So that's a general relationship for acceleration of one point relative to the other. And we're going to use all of the information we have. We're going to use the instant and time, and we're going to work out expressions where we can solve for all of our unknowns. So what are we're going to do a little laundry list of unknowns. We're going to have acceleration at point A, which is, lucky for us, only in the i-hat direction, because A is scooting along on this horizontal surface. It has no component, it's not flying up off of the ground, it's not sinking down into the surface. So just like B is moving straight down the wall, A is moving straight across the surface. So this is good for us. We could probably also say it's moving in one known direction. We're going to have velocity of A, we know that's also in the i-hat direction, and we're going to have to solve for omega and alpha of the rigid body. So those are the things we're going after, and we've already invoked, by stating that the acceleration and velocity of A are only in one vector direction, we've already used one relationship about the geometry in our favor. So we've kind of invoked one equation already by just scribbling that down, but that's kind of by observation. So let's start with velocity, because we are going to use our relative velocity expressions to get an expression for omega, which we will then need to relate our accelerations of one point to the other. So let's write an expression for velocity at point A relative to the velocity at point B, plus omega ladder crossed into R from B to A. Okay, so we can use the geometry, our 30 degrees, to get radius vector from B to A, and then we'll also need to pick up the length of the ladder there. So our RB to A, when we write that out, we get 16 feet cosine of 30 degrees in the I hat direction minus 16 feet sine 30 degrees in the j hat direction. That's just applying the trig. We can multiply that and just get numbers. This is an unknown, and this is negative 4 feet. And actually, I needed to establish a coordinate system before I could say what that radius vector was, because those didn't make any sense without a coordinate system. I missed a very important first step. And in fact, in this case, I'm going to break with my typical convention, and I'm going to write I to the left instead of the right. So J hat is positive upward, I hat is positive to the left, not to the right, which means basically my positive omega and alpha direction, positive increase of theta for my rigid body rotation is going to be clockwise, not counterclockwise. So if I go from B to A, I'm going in the positive I hat, negative J hat, which is why I have those written. So VB is in negative 4 feet per second J hat. So I can use the fact that the velocity at point A is only in the I hat direction, so I can say V sub A, magnitude of the velocity, I hat, is, I can relate that just to the I hat components, and to do that I'll have to work out the cross product. So if I do that, let me just write out the whole thing here. We got all the components still. So there's V sub B plus omega. I end up with 16 feet cosine 30 degrees, and then I'm going to have k hat cross I hat, which gives me j hat plus omega times negative 16 feet sine 30 degrees times negative I hat. So this is working out the cross product. So now this gives me two equations, so I can use that to solve for velocity, the magnitude of the velocity at A, and omega, the rotational velocity of the ladder, how fast it's rotating basically about its own center. So to do that, I just basically separate components, the different variables. So relating just I hats to I hats, I can say velocity, the magnitude of the velocity of A is going to be 8 feet times omega. So I've still got two variables, and then I'm going to use the j hat component of A, which is 0, to solve for omega. So I can say 0 equals negative 4 feet per second, referring to my notes for my calculations so I don't have to do those again, plus omega times 16 feet cosine 30 degrees. Cosine 30 degrees. So solve for omega, angular velocity, and I get 0.2886, give or take, radians per second. And that might have been one of the points asked for in the problem. I don't remember, but regardless, it's something we need to go ahead with our acceleration relationships. Now I could plug that in and get the velocity at point A as well if I wanted to. To get acceleration, though, really I only need this. So that was an important step, and really that's all. If I'm looking for acceleration at A, this was all I needed. This was the only reason I needed to go through the velocity relationships, was to get that at that angular velocity of the ladder, because I'm gonna turn around now and say the acceleration at point A, which is a vector, is the acceleration at point B plus the angular acceleration of the ladder, alpha, crossed into our B to A, minus the magnitude of the angular velocity of the rigid body, which we just solved for here, squared, times our BA. This is my general expression for the acceleration of one point on a rigid body undergoing planar motion relative to the acceleration of another point on that same rigid body undergoing planar motion, and the angular acceleration and velocity of that rigid body. So it's kind of our go-to expression to relate acceleration of 2 points on a rigid body undergoing planar motion. So we're going to do the same exact thing we did before. We're going to plug in what we know. This is, of course, two expressions in one. There's an I hat component and a j hat component of this expression. So basically this is two equations. And and we're going to again invoke the fact that the acceleration at point A only has a component in one direction. So we basically have two equations here, and we have the unknown alpha, and then we have the magnitude of acceleration, because we already know the direction. It's only in the positive I hat direction in this case. So two equations and two unknowns. At this point, we pretty much have the problem. You could say we've solved it. We just have to plug in and crank through a two equation, two unknown mathematical expression. So we could say that the crux point, in terms of the key point on this, was first knowing that we have a rigid body undergoing planar motion, which means we can use this relationship and this relationship to relate velocities and accelerations at both points. We are given quite a bit of information with regard to what's going on at one point. And then the other key point is we had to recognize the direction of velocity and acceleration at the unknown point. We had to know that it was going only in one direction. It didn't have to be purely in one unit vector direction. It could have had components in two, but we had to know its direction. That effectively eliminated another variable. So let's go ahead and put that to use and walk through the solution. So we'll just do some mathematics here, and I'm gonna multiply a few things out. So we're going to we can say that acceleration, the magnitude of acceleration of at point A, it's all in the I hat direction. That's going to equal -2 feet per second squared. J hat, that's acceleration of B, plus alpha crossed into RBA. So I'm just going to write out the result of that cross product. That ends up being alpha times 13.86 feet in the j hat direction, plus alpha times 8 feet, -8 feet in the negative I hat direction. So that's the result of this cross product here. And then we've got negative 1.1547 feet per second squared. I hat plus 0.6666 feet per second squared j hat, and this 2 term is omega squared times both vector components of our RBA. So you square this and then you multiply it by these two, and then you put a negative sign in front. So now all that's left to do is collect I hat terms and set them equal to the magnitude of the acceleration at A, and then collect j hat terms and set them equal to 0, and then solve for A and alpha. So if we go ahead and do that, we can say, I'm just going to keep the I hat so I remember what's going on. And I'm going to browse around and say, okay, I got 2 terms on the right hand side of this equation that are going in the I hat direction. And these are, I've got 2 negatives, so I've got alpha times 8 feet I hat, and I've got plus negative 1.1547 feet per second squared, also in the I hat. So 2 unknowns. Now I'm going to write the j hat components together. So in that case, I'm going to have 0 on this side, and I'm just going to take that 2 feet per second squared. So I can say I have 2 feet. Notice all of my units are making sense. I've got 8 feet. I know omega is going to be in radians per second squared, so I got feet per second squared, and I got feet per second squared. So that's reassuring. As I work through, one sure sign of a mistake is if the units aren't matching up. So that would just tell me to go back and look to see where there was an error. So this is going to be alpha times 13.866 feet j hat, and then we have this term over here. We have the 0.6666 feet. Something was a 2/3 term somewhere. Okay, so from this we can solve for our angular acceleration, and we end up getting a positive number, which means it's going clockwise, because positive alpha is in the clockwise direction. So we get a 0.0962 radians per second squared, and now we can, I'll change color, we can plug that in right there to solve for the magnitude of the acceleration of point A, and we end up getting acceleration of A is 0.385 feet per second squared. This ends up being a positive number, which means it's going to the left, which is exactly what we would expect. As this point comes down, this point's going to go over to the left. So it's interesting that this is a much, kind of seems like a much smaller number than you have up here. The ladder is rotating. So again, key points are fundamental relationship between 2 points, velocity of 2 points on a rigid body undergoing planar motion, ditto for acceleration of those 2 points, and a knowledge that one point had a known direction, and then of course given the parameters for the other point. So that was what allowed us to solve this problem. Very basic, 2 points on a rigid body undergoing planar motion, and then knowing what's going on in terms of the geometry of the problem, and direction of motion at that instant of your unknown point. So that is it for this mini lecture, and stay tuned for more kinematics of rigid body planar motion.